All right, so we're saying welcome as we continue the oxidation and reduction class. We just want to move into the oxidizing agent and reducing agent. Now, CXC sometimes ask you about what is happening to these two agents. Now, if something is an oxidizing agent, one of the things that, or a reducing agent, one of the things that as a student, we want you to understand is that if you put a oxidizing agent with another oxidizing agent, you won't have a reaction. Likewise, if you put a reducing agent with another reducing agent, you won't have a reaction. You do, though, have some compounds that act as both oxidizing agent and reducing agent. Now, if you basically have an unknown substance, so you have an unknown substance in a beaker. If you want to find out if this is an oxidizing agent or a reducing agent, what you can do is then react it with a known oxidizing agent and a known reducing agent. And of course, you look for the results or the observation to identify if it's either of those, a oxidizing or a reducing agent. Now, like I said, CXC likes to, question you. So one of the things that they like to ask is, what is happening in terms of electrons? So what is happening in terms of electrons with the oxidizing agent? And so as a student, you should remember that the oxidizing agent is being reduced. And if it is being reduced, then it simply means the oxidizing agent is gaining electrons. So you just have to have a little reasoning. Once you understand the whole concept, we did say that if something is being oxidized, then it is the reducing agent. And if it's being reduced, it's the oxidizing agent. So on the flip side, if you want to think about any of those, you use that. They might ask you as well, then what is happening to the oxidation number? And of course, likewise, we go back to the reasoning. We know that the oxidizing agent is being reduced. And so, if it is being reduced, then you have a decrease. And the beauty about oxidation and reduction for me, as I said, they operate simultaneously and usually they're opposites. So the reducing agent is being oxidized. And if I'm being oxidized, then we know oxidation is a loss of electrons. So the reducing agent is losing electrons. And then, of course, we made mention about the oxidation number. And again, if we know anything about it, oxidation, since it's being oxidized, then you're going to have an increase. So usually these questions may come as 1 mark questions just to ensure or to test your knowledge if you know what is happening with the reducing agent, if you know what the concept of oxidation and reduction is. And so just have this in the back of your head. Once you understand this, then you would be able to interpret and answer questions. We're going to be looking at some of the popular oxidizing agent. And so as we said before, once they are with a reducing agent, they will basically have a observation that you can look at or observe. Acidified potassium manganate. That's the first one, the oxidizing agent we're going to be looking at. So acidified potassium manganate. Now, remember we did the whole concept of assigning or working out the oxidation state. And so the acidified potassium manganate, we put it in bracket, the 7, and we use Roman numerals because we want to tell persons that the oxidation state of the manganate currently is a +7. Yeah? Now, what did we say that happens to a oxidizing agent?
Reduces,
Go again.
reduces,
So it reduces. Beautiful. So this is it. And if you want to, we're really focusing on this. So let me zero in, put a little color to this, because a lot of times, sometimes the students don't have the whole story behind. So I like to ensure that, we have an understanding, not just to just tell us, say, oh, this is purple, this turned colorless, and whatever. We have to learn to appreciate what we learned and applied. So we have learned how to assign oxidation number. Can anybody talk about why this manganate ion basically has the oxidation state of +7? Well, if you're able to, you should be able to see. Now, one of the rules are, we know that the ion, the monoatomic ion, the oxidation number is the same as the charge of that ion. And so definitely the potassium is a +1 because its charge as an ion is a 1 plus. We know as well that oxygen is technically a -2 in terms of its oxidation number unless it is bonded with a peroxide. And in this case, it's not with a peroxide. And we also know that when you add, this compound is a neutral compound. We're not seeing any charge. Don't look at the acid that we mix it with. We're not seeing any charge on that potassium manganate. So it's a neutral compound. So when you add the potassium, the manganate, and the oxygen, the overall atoms in that compound oxidation number, it should equal to 0. So we know that the overall for the oxygen is going to be 4 times 2, the negative 2, which is negative 8. Now when we look at this, as I said, if you have a problem in working out, you can look at the previous video to see how we work this out. So the manganate would have been A plus 7, because now you have plus 8 minus 8 equal to 0. So we now know that the manganate is basically a plus 7. Now, if we take this acidified potassium manganate, and let me just make mention now that it is purple in appearance. So this is purple. And so we have a compound. If I take another oxidizing agent, or if I have an unknown compound and I have an oxidizing agent, and I react it, put it with this potassium manganate, it's just going to remain purple. And so more than likely, we would know that that unknown substance is also a oxidizing agent. But if you put it with a reducing agent, so we know that a reducing agent, it will cause another compound to be reduced. So when you put this oxidizing agent, the focus is going to be on those manganate ions. They are going to be reduced. A matter of fact, when it reduces, it becomes a manganate 2 plus. So, and of course, we can see why we use the term reduction, because it was plus 7 and now it's becoming a plus 2. The oxidation number will decrease. So whatever you put it with is a reducing agent, because it is causing the manganate ion to be reduced. Now what would you see? This manganate plus 2 ion is actually colorless. So what you find is that it will move from a purple to colorless. So that signifies that you have placed the acidified potassium manganate with a reducing agent. So acidified potassium dichromate is another popular oxidizing agent. So let me zero in on the dichromate. Now again, we're looking at a neutral compound. So we know that when we add the oxidation numbers of all the atoms, you should, when you sum it, you should end up with it being equal to 0. So we know that each potassium is actually a plus 1. We have 2 of them, so they are plus 2. Now, the oxygen, we have 7 of them, right? And so it is 7 times the negative 2, which gives us, right? right? So when you add these, so if you go back to working it out, where you have these all these oxidation number, if we want to get this to be equal to 0, then of course, I mean the both of them, because remember we have two chromate ion, the both of them will equal to a positive 12. And so since this is a reflection of 2, then we would appreciate that one of the chromate ion, because remember we said that when we speak in terms of the oxidation state, one of them would basically be a positive 6. And it would have been what we see in the name. We did say that when we want to talk about the alternative name, what we do is to put the Roman numerals in terms of the oxidation number. So this represents 6. So we know that the dichromate or the chromate ion is a plus 6. Now, again, we're looking for that concept of a color change. Now, this is basically is in terms of the appearance, it is kind of orange red, but closer to orange. So we know that it is orange. And since it is orange, once you react a other oxidizing agent with it, it's just going to remain orange. But if you put it with a reducing agent, what the reducing agent will do is to reduce the chromate ion. So it's going to move from a plus 6 to a plus 3. Now, when it moves from a plus 6 to a plus 3, that appearance of the chromate ion is green. So when it is reduced, it moves from an orange to a green appearance. So again, once it is with a reducing agent, we know that the reducing agent is going to cause the oxidation state or the oxidation number to reduce. So it moves from a plus 6 to a positive to a plus 3. And so you get that color change from orange to green. So if you have an unknown, and sometimes teachers will use this as a planning and designing lab, maybe students in the class now may have a planning and designing lab in such a case where you're asked to identify given substance as being oxidizing or reducing agent. And so what you have to do is to plan, and you would actually, react them with a known oxidizing agent and a known reducing agent. So in this case, the acidified potassium dichromate, when you have that chromate ion being a plus 6, it has that orange appearance. But once it is reduced to the plus 3, it's going to change from a orange to a green. And so that will indicate that it is now with a reducing agent. As I said before, if you put it with the substance and nothing happens, more than likely, you can deduce that it's basically probably with a oxidizing agent. So in other words, if I put acidified potassium dichromate with acidified potassium manganate, nothing should happen in terms of their color. Cool. So the next popular oxidizing agent that we can look at is the iron 3 salts. Now, we know that salts basically have an anion. It is when the concept of the acid, the hydrogens are replaced by a metal. So iron salts, basically iron 3 salts, the metal would have been iron, right? Now, the thing about this, and I may not have explained it in the first two, so after I do it, I can go back to those to show you. Now, we know that, again, a reflection of the oxidation state is what we have in bracket. So iron 3 simply means that the oxidation of the iron is a +3. Now, the appearance of that is a yellow brownish appearance, yellow to brown. So once you have a salt that contains the iron 3 ions, it's going to have that yellow brown. And of course, you'd have used an aqueous because you'd have to ensure that the ions are able to move, so you dissolve it in water. Now, if you place that with another oxidizing agent, you're not going to have anything happening. But the moment you place it with a reducing agent, what you find happening is that the iron becomes Fe2 plus. It forms the iron 2 ion, and that in itself has a pale green appearance, and so it changes from yellowish brown to pale green. We would have not spoken about electrons in the previous ones, but this is more fitting. We can look at it in the others as well. Now, the iron, what this says about the iron 3 plus is that we know it has lost 3 electrons, and that's why you have that oxidation number. It now has 3 more protons than electrons, and so it has that positive charge. But what I want to indicate, and sometimes students are not understanding this, if I move from a 3 plus to a 2 plus, it simply means that I'm getting back one of the electrons that I lost. And again, the reducing agent that we would have mixed this whatever Fe3 plus salt with would be causing it to become reduced. And we know that reduction is the gain of electron. So technically, the iron is gaining an electron, and that is why it is moving to a 2 plus. That is why we would have seen that appearance come from a yellowish brown to a pale green. Likewise, we know that it is being reduced, and so we have a reduction in the oxidation number. It's moving from a +3 to a +2. And like I said, I may not have mentioned it before with the other two, but we can go up and talk about it. So the chromate ion was a +6. And again, that would have meant that, it has lost those 6 electrons. So when it comes in contact with that reducing agent, the reducing agent is going to cause it to become reduced. And we know reduction is a gain of electron. So what happened to the chromate ion? It basically gained 3 electrons. And that's why it became a 3 plus. And of course, again, we saw the reduction in the oxidation state. So moving from plus 6 to a plus 3. Same for our manganate. Our manganate ion was a plus 7. When it was mixed, or if it is mixed with a reducing agent, what it will now do is to have a gain of electron. Would you be able to tell me how many electrons it gained? So if it moved from a plus 7 to a plus 2, how many electrons did it gain?
5.
5. And so now, because of this concept where it gains the electron, it's now in a new oxidation state. And this state, it is one where the ion appears colorless. So that's why we have that change from purple to colorless. Right? So that would have been those that we looked at in terms of, I never really speak in terms of the electron. So the next oxidizing agent would have been the sodium chlorate ion. Now, as you can see, we have a 1. Sorry. We would have known that the chlorate is a negative 1, and we can work it out. We know that the sodium is a plus 1. The chlorine is a minus 1. In this case, basically a plus 1 as well. And we remember that the oxygen is a negative 2. So when we add all of those, we get the 0. Now what happens is this. When you think of your bleach, and so sometimes you have a little white clothing, your white shirt or your white dress, and you may get a stain on it. That stain may be colored. What this will do is, since it's an oxidizing agent, it's going to oxidize the dyes. And when it oxidizes the dye, it basically causes the dye to become colorless. So usually, when you have your clothing and you may spill some ink or something on your clothing, you tend to allow it to soak in the bleach. And the bleach itself will whiten the dye, oxidize it, causing it to become colorless. And so sometimes you have to be careful in terms of what you put your bleach on, because if you put it on your colored clothing directly, what it will do, it sometimes even forms oil. We're not throwing no word for nobody, but so sometimes you may see the clothing start to develop some little holes inside of it. And it is due to how we go about washing it. And so you have to be careful when you're using the bleaching along that line. Likewise, you may see it lighten some areas of the clothing. So say it does look white out. And so that would have damaged your clothing. That's not going to be looking good. You have a nice red dress. you know you can't put the bleach on it directly. Some you have um, formulated bleach for these type of garments, the colored. And that's one of the reasons why even when we are washing, today or Sunday, maybe persons are doing their little washing as well, or later them are going to do that. The concept of separating. So with dark, we white, and we colored, we don't wash them together because of this very same reason. So if you're utilizing the bleach, the fabric will be of interest. So some fabric just can't take it, and after you wash it with the bleach, you technically have a situation where you may see holes. So technically, it just oxidizes. It's an oxidizing agent, and so it oxidizes the dye, causing them to become colorless. And that is basically one of even the major applications of oxidation and reduction in real life. So for this oxidizing agent, when you mix it with a reducing agent, what will happen is that you're going to have a pungent colorless gas evolving. And so CXC can basically even ask you in terms of, say they give you a known reducing agent, and they say that this, because what you need to understand, they can tell you that a reducing agent was reacted with a substance, and this is the observation. You're supposed to know which oxidizing agent is it. So if they tell you that a pungent gas, colorless gas evolve, right? You should know that the only way you would get that gas is if the oxidation, is if the compound or the oxidizing agent in question is concentrated sulfuric acid. Acidified manganate will not give you that gas or that pungent smell. Acidified dichromate will not do that either. The chlorate, sodium chlorate, will not do that. The iron 3 will not do that. So at the end of the day, you should be able to identify the oxidizing agent based on the observation, because that's how they may come at you at times. So they just tell you the observation, oh, we basically saw the substance moving from purple to colorless. Right away, as a student, you should know that the oxidizing agent is the potassium manganate. They will also sometimes ask you to give reason. So along with knowing the explanation about the fact that you have the manganate ion moving from a +7 to a +2 is also critical, if it is that they ask you to explain why that color change happened, or give reason, deduce, account. When them say account for the color change, that's what they're looking for. They want you to tell them that it was a +7. If it was in the case of a potassium manganate, that's what they want to hear. Cool? So once you see anything about pungent gas being evolved, then you know the formation of the hand. Go ahead.
Yes, sir. Can you repeat waiting for why the concentrated sulfuric acid?
I didn't hear the question.
Can you repeat why the pungent colorless gas was produced? The part that you said that was accounting for it. Can you repeat that, please?
So, we I'm saying they may just give you the concept of the observation. So they will tell you, they might give you a scenario and say that student John or whoever in the lab, they took a reducing agent and react it with an oxidizing agent, and the observation is a pungent colorless gas evolving. Now, the fact that he would have seen that observation due to smell. Well, him can't go see the gas, so it's a colorless, so he would be smelling that pungent odor, is a result of the oxidizing agent being concentrated sulfuric acid. Why? Because it's the only oxidizing agent that produces sulfur dioxide. So the sulfur dioxide is technically what you have in terms of after you have that reduction. Now, if you can recall in my previous videos, if you remember, we said that, you see, reduction initially, scientists look at it in terms of the loss of oxygen. Now, when you think about sulfur dioxide, the formula looks like this. So again, we can appreciate the concept is about that sulfur. Remember, in this case, now we can work it out. What is the sulfur in this case? We know that oxygen, all of the oxygen is a -8, right? These
Right,
two
sir.
would have been a +2. Again, this sulfuric acid would have been a neutral compound. We're not seeing any charge. And so we appreciate that this sulfur is a +6. Must be a +6. That's how we're going to have it equaling to 0. Now, as I said before, reduction is basically a loss of oxygen. That's one way we can describe it. So if you look at this, the sulfuric acid, it would have had 4 oxygen, but when you look at the sulfur dioxide, it now has 2 oxygen. So the loss of oxygen, and I wanted to just highlight that. So outside of looking at the fact that the sulfur right here would have had a reduction in oxidation number, let's talk about it as well. This would have mean that this is a -4, the 2 oxygen. So this must have been a +4. So we recognize that when you think about what is happening with the sulfur, it would have gained 2 electrons. We would have seen a reduction in oxidation state. We would have seen where the compound has lost oxygen. Those are the 3 ways that would have identified, right, that the compound would have basically been reduced. So again, make the connection. The sulfur, or that sulfur dioxide, is what we use to account for the fact that the oxidizing agent would have been concentrated sulfuric acid, because again, potassium manganate, potassium dichromate, none of those will give you any pungent gas, colorless, like that. Cool?
Yes, sir.
So when we look at dilute concentrated nitric acid, too can act as it too is a oxidizing agent. And so when we look at this, we recognize this would have been a +1. Matter of fact, that oxygen, how much is that? 3. So we know that that is a -6. So we know the nitrogen in this case is a +5. Not true. True. When we look at the nitrogen dioxide, we know that the oxygen, the both of the oxygen would have been a -4. So this must be a +4. And again, we see the concept. We know reduction is a loss of oxygen. So we see where the compound is losing oxygen. We see where the nitrogen is technically gaining electron. We see where the oxidation state of the nitrogen is being reduced, moving from a +5 to a +4. So again, all you need to know, remember, is the outcome, the observation of all these oxidizing agent when you place them with a reducing agent, because that is what you're going to be using to determine in case they just give you the observation. So a lot of times they can bring it in a table, they give you the observation, you should know what oxidizing agent would have given this observation, because none of them give the same. So even though the sulfuric acid and the nitric acid produce a gas, please note the pungent smell due to the sulfur dioxide and the fact that it is colorless versus the brown gas evolved with the nitric acid, and we don't mention anything about any pungent, right? Cool. So those are the common oxidizing agent, and you need to know the concept of as to why or how we know or how we give account for those observation. So when we look at the reducing agent, the first one we're going to examine is potassium iodide. Now, we need to remember what is happening to a reducing agent in terms of oxidation and reduction. So a reducing agent is being oxidized. Yeah? And remember, oxidation is the loss of electron. So watch us now. The potassium iodide is colorless. And if we really check back what happened, you find that the, the potassium is a +1, and of course, the iodide is a -1. Now, say for example, it is reacting with a oxidizing agent, what you're going to find, especially like something like the sodium chlorate or something that has in chlorine that is more reactive than the iodide. It's going to take its place. And so what you find is that the iodide is going to be picked off, forming that, going back to the atom state. And if you can recall, what would have happened between this potassium and the iodide is that the potassium would have given the iodide a electron. And so when whoever that is more reactive that come amongst the iodide is going to force it to take back, or sorry, give back that electron that it took. So now that happens, the iodine will basically be present in the solution, and that is what gives it the brown appearance. That's what we're looking for. Now, simply put, we know that there's an increase, and the concept is iodine, when it is not bonded in this state, can somebody remind me what would be the oxidation state of the iodine here? What would be the state of the iodine, oxidation state? I2. Anybody? Somebody? What is the rule?
There zero.
So 0. So we know that any element that is not bonded to another element, in this case, we also take into consideration the 7 diatomic elements. So once they're like that, 0. Again, we said that the reducing agent is being oxidized. Oxidation is a increase. And a lot of times students sometimes just make a little misconception because it's -1. If you think about your number line, you're actually moving to 0, so you're actually increasing. Because choose a person says see the 0 and they must say, sir, but that's a 0. But remember, you're coming from -1. It's like you owe somebody something and you pay them back, don't owe them anything, so you're at 0. Yeah? So it would have been a increase in oxidation number. Again, what would have happened is that that electron that the iodine would have accepted from the potassium, whoever is coming that is more reactive would have caused it to basically give back that electron, and then they take it from the potassium, and so you find that it goes back into the atom state where it no longer has that one electron. So we know oxidation is the loss of electron. And so the observation we're looking for now that it's no longer bonded, then you're going to see the evidence of the iodine in the solution, which gives it a brown appearance. Yeah? So the next one we're looking at as a reducing agent is Mr. Iron 2. So bear in mind the iron 2 salts. So the iron 2 salts, they are the reducing agent. Do remember that the iron 3 are the oxidizing agent. And so these two, you can have some little connection with them. So remember, the presence of the Fe2 plus ion is that they are pale green. Yeah? And so what you find happening, remember, it's going to be oxidized, and so it gets oxidized to a 3 plus. It gets oxidized to the iron 3, right? And so a lot of times when you think about an application again, in terms of your grill, your one of the things that we do even in the Christmas period, yes, it helps with beautification. You paint back the grill and you did all of that. Christmas gone, nice up the, bring a little more vibrant to the yard space. But the thing is, the paint, one of the chemistry, because a lot of students don't understand that it's chemistry again, real life situation. The paint, what it does is to provide that coating over the iron. And how is that beneficial? It is preventing oxidation, right? Because remember we said that, metals undergo oxidation because metals lose electron. So what you find is that the paint will basically help to reduce, because it not going to prevent it. So even if you're in the school system and you look at the chairs, one of the things that we do is to paint the chairs. And so that will help preserve it. And I said in the real life scenario, most of the time when we have our metals, we have to paint them. And so it provides that protective coating over the metal. And what it also does, it doesn't allow for oxidation, or it reduces, or what's the word I want to use? It hampers or slow down the effect of oxygen reacting with the metal. But eventually, if you have the oxygen reacting with the metal, you see that brown, you ever touch a grill, or with your white again, and you see how this is so real life situation. You pass against the grill that was oxidized because the metal would have now been reacting with the oxygen, and so it caused that brown flaky stuff to be there. So you touch your white clothes, that brown flaky stuff gets on your white shirt. You have to now go and get, right, that reducing agent or that oxidizing agent to help you to get out that brown thing out of it. So what you find is that the pale green becomes yellowish brown. And that is due to the fact that we are now forming the Fe3 plus ion. So the concept is, again, when you look at it, there's an increase. There is an increase in oxidation number. Again, if you think about Fe2 plus ion, this would have meant that the ion lost 2 electrons. And so if it moved from Fe2 plus to Fe3 plus, it simply means that it lost another electron. And we know that what is happening to a reducing agent is that it is being oxidized. So it's losing electron. We see the increase in oxidation state. So it moved from a pale green to yellowish or yellow brown appearance. So for these two, you have to note the observation. Look at what it is moving from, and that will help you. So is it moving from a pale green to yellow brown, or a yellow brown to pale green? That will help you to note if you're dealing with the Fe2 plus, which are salts of reducing agent, or the Fe3 plus, which are salts of the oxidizing agent. Cool? So the next reducing agent that we can look at is the hydrogen sulfide gas. And if we want to talk about, again, the concept of these two, remember I told you that, sulfur, nitrogen, and carbon, they are, let me not use problem, but they are the ones that have that change in their oxidation state based on where they're at. So you have to be careful with them. So see it here. We have seen where it is a +6, a +4. Now we're seeing it as a -2, right? And so what happens is that when it comes in contact with a oxidizing agent, it basically is forced to accept the electrons. Sorry, it basically loses the electrons that it accepted. So it accepts one electron from each of these two hydrogen ions, right? And so whenever it's oxidized, it's going to give up, because we know oxidation is the loss of electron. And so when it gives it up, it's going to go back to the solid state. It forms solid sulfur, which is a yellow precipitate. Now we know any compound or any atom that is not bonded. So what would have been the state? What would have been the state of this sulfur, of the oxidation state?
Yeah.
So 0. So again, we're seeing that 0 and that negative. Please remember about your number line. If I'm moving from a -2 to 0, I'm increasing. So we know an increasing oxidation number is oxidation. Also, as we said, these two hydrogen ions would have given the sulfur the 2 electrons. Now, the sulfur is being forced to give up, lose those 2 electrons that it got. We know the loss of electron is oxidation. So again, if you notice all of these, whether the reducing agent or the oxidizing agent, everybody has a different observation. And so it's the observation that you are given that will help you to determine if you're dealing with a particular reducing or oxidizing agent. It's the observation that will help you to account for the observation. So basically, once you get the observation, if you see anything about any yellow precipitate forming, nitric acid can do that. Sulfuric acid not doing that. Dichromate is not doing that. So it leaves you to just know them. I tell students, know the observation. Once you know them and you can explain why they occur or explain or account for them, then you'll be in good standing, because these are the ones that they will provide you with. They won't go outside of these. So these are the popular reducing. You have more, but these are the ones that are, mentioned by the CXC syllabus that you should know as a student. Cool? So we have one more reducing agent. So for this reducing agent, again, if we're supposed to assign, we know this would have been a +1. This is a -1. And of course, what happens when it comes in contact with an oxidizing agent? This chlorine would have accepted an electron from the hydrogen. And so the problem is that whatever oxidizing agent is going to force this chlorine to lose the electron. Now bear in mind, hydrochloric acid, it's basically colorless. So when it is forcing that chlorine will basically go back to the atom state, which forms chlorine gas. Now the thing about chlorine gas is that it is yellow-green in its appearance when it evolves. Again, notice we talk about a brown gas, we talk about a clear or a colorless gas. You need to remember that none of these give the same observation. So at the end of the day, again, I can't stop emphasizing it. You just need to know the observation. So what really happened is that we see where the chloride or the chlorine or the chloride became the atom where it lost the electron that it gained, and so it becomes a zero. So it's moving from a negative one to zero. The oxidation number would be increasing. We know oxidation is occurring. So it lost an electron. I think it is coming from 2026. Sorry. 2016. I'm run gone in a day in a Awagam 2026. So 2016. Now again, let's see if we can put what we have learned into practice. So it says distinguish between an oxidizing agent and a reducing agent in terms of electron gain or loss. Yeah? We said that if I am a oxidizing agent, I am being, come on, what's happening to me if I'm an oxidizing agent?
Reduce.
I'm being reduced. And you're in the exam and you're smiling and you're saying to yourself, yeah, thank you, Mr. Thomas, for teaching me this. Not true. Now, if I'm being reduced, remember they said they want to talk to you, they want you to talk to them about either it is loss or gain. And from you get to this, we know that reduction is a finish.
Gain of electrons.
Beautiful. Remember, I said that, I like to do it like church, when the pastor says, and so God so loved the world, and the congregation would finish. So that's how we're dealing with it. So if I say reduction, suppose we can finish the line because we know it. Yeah? So is the gain of electrons. Yeah? And then we're supposed to talk about the reducing agent. If I'm a reducing agent, what is happening to me?
Yes.
Unfortunately, I didn't hear that.
You're being oxidized.
Thank you. And so we know oxidation. Over the congregation there. Oxidation.
So
You might keep checking.
There's a lot of electrons.
Yeah, beautiful. So we are smile and we get our 2 marks. Not true? Every mickle make a muckle. Jaden. No, not the youth from TikTok. Jaden carried out some tests and recorded the observation in table 3. So Jaden did their work and he used this information to answer the questions that follow. So here in test, an aqueous solution of C was added to acidified potassium manganate. Acidified potassium manganate is what?
an oxidizing agent.
So it's an oxidizing agent. See, we learned that. And so look at the observation. A matter of fact, they could have even given you this observation and you supposed to know, say, acidified potassium manganate in the react it with. So, but they give you what happened. Potassium manganate 7 solution changed from purple to pale pink. Yeah? Yeah?
Sir.
And
Yes, sir.
in the second one, an aqueous solution of C was added to a solution of potassium iodide. Potassium iodide is a what?
Reducing
See? So we understand. Because see it there now? We know that whatever C, right? Right? We basically have the potassium iodide solution changing from colorless to brown. Now it says for this part, a strip of iron was placed into an aqueous solution of copper 2 sulfate. A blue solution faded and a brown deposit settled. Now, even though this is a little bit in terms of oxidation and reduction, right here, you have to know some knowledge about the concept of the reactivity series. Now, iron is above copper, and the rule is any element that is above another element can displace it. So right here, what is happening is that the iron is displacing whoever the copper from the sulfate, forming iron sulfate, and so that's why you see the blue solution is fading, and you actually have now a brown deposit. Look at this again. A strip of silver was placed into an aqueous solution of copper 2 sulfate. In this case, the solution remained blue. Now the thing about it, silver they down here, so silver is not able to displace copper, because as I said before, in terms of the reactivity series, so it goes like this is supposed to be Na, calcium, magnesium, aluminum, zinc, lead, sorry, iron is supposed to be above lead. How? So hydrogen, have a little jargon that I use to remember. So this is our reactivity series that we're speaking about right here. So if the element is above, then it is more reactive, so it can displace. So as I said before, silver is here, copper is there, and so you basically have it. So I miss out the copper here. So we basically have a situation where the copper is higher than the silver, and so the silver is not able to displace the copper. but the iron is higher than the copper, and so it's capable of doing that. The question says, look on this quick one mark. Quick one mark. State an oxidizing agent that is not mentioned. Not mentioned.
And
No, that is not one. The baby made a talk.
fluorine gas.
Huh?
Fluorine gas.
Fluorine.
Fluorine.
But we didn't mention, remember, an oxidizing agent.
Nitric acid.
So you could have mentioned nitric acid. What else?
Hydrogen peroxide.
So Miss gone out of the ones then what we just mentioned. So remember the ones that we spoke about are the ones that we would have given the observation and we deal with how it happens. So what were they?
Concentrated sulfuric acid.
So we have concentrated sulfuric acid. What else? Could I mention?
Sodium chloride.
Sodium chlorate. What else?
Potassium dichromate.
Potassium dichromate. Right? We were asked, if we look back, this one, C is acting as a,
Reducing agent.
and we know that because we see that the manganate 7 is being reduced.
Used.
All right. What is it acting as in test 2?
Oxidizing agent.
So it acting as a oxidizing agent because we're seeing the potassium iodide solution changing from colorless to brown. So that would have meant that the iodide, right, is being displaced from the potassium, causing it to become the atom. Yeah? With reference to oxidation states, explain each of your answers in B. So basically, this is where you're going to, again, what did we say happened to the manganate ion? And they said with reference to oxidation state. So they don't want to hear about electron when you talk about oxidation state. So the manganate ion was a +7 and it moves to,
+2.
and so the oxidation state, what happened to it?
It decreased.
Increase.
Right? And we get the 2 mark, that's so. Coming down again. we would have had who in test 2? Who in test 2? The potassium iodide, not true?
Yes, sir.
Sir.
And we know that that potassium iodide, so it is moving from a negative 1 to 0. So what is happening to the oxidation state?
It increased.
Write an ionic equation with state symbols for the reaction which took place in test 3. What was test 3 again? Test 3 spoke about the strip of iron, right? Placed in aqueous solution of copper 2 sulfate. So they want an ionic equation. Now normally, if you're having problem, you start out with, I can do the long, I wonder if I have space. Probably I can do it down here. So we know the iron, right, which is a solid, plus the copper sulfate, which is aqueous, is going to give us, what is going to give us?
Iron sulfate and copper.
Iron sulfate, aqueous, and
Copper.
copper solid, right? We have to ensure that the equation is balanced. Is it balanced?
Yes, sir.
Yes, sir.
And we know to write our complete ionic equation, we say that we break up all the aqueous. We cannot break up the solid, the liquid, the gas. So we're writing back this as is the copper 2 plus aqueous plus sulfate 2 minus aqueous gives us iron 2 plus aqueous plus sulfate 2 minus aqueous plus copper solid. And then we said that we look on both sides of the equation for the spectator ions. So the ions that are just there, they're not taking part in the reaction. Which ion is that?
The sulfate ion.
So we eliminate the sulfate ion. Bear in mind, this is the equation that CXC wants in the slot. But I'm showing you how we get to that equation. So if you didn't know, and you're in, so this is what we want to have. So sorry, this is supposed to be an E. Right? And so this, hope you're seeing it clearly. I know it's a little bit of struggle to write with this pen, but iron solid plus the copper 2 plus. So a lot of times I tell students to remember the state. So what are the things that we need to remember for a ionic equation. For an ionic equation, we are writing ions. So we're breaking up all the soluble compounds that you need to know the solubility rules. So we know some of the rules, the group ones, sodium, potassium, and ammonium ions. Once you see them in a compound and the nitrate ions, the compound is going to be soluble. We have some other rules that govern the other compounds. So for this, you have to know the solubility rule. Also, since the solubility rule, it will help you with the state, because they're going to ask you for state symbol. Also, you should know how to balance a chemical equation. Fortunately, this one didn't need any form of balancing, but you might be required to do that. So you have to know the concept of how to. And then, of course, you follow the concept, you break up all the aqueous compounds in the equation, you write back the solid, the liquid, and the gas as they are. And once you do your breaking apart, you would have eliminated the spectator ions, and then this is our ionic equation. Yeah? And of course, 2 marks, usually 1 mark for the correct state symbols and 1 mark for the correct balance equation. With reference to the electrochemical series, explain the difference in observation between test 3 and 4. And I think I went through an explanation already, but just to go back, we said that a matter of fact, in the electrochemical series, calcium is before sodium. So in the reactivity series of metals, sodium comes before calcium. So since this is the electrochemical series, calcium appears before sodium. Now, any element that is above another element is capable of displacing that element from a compound. So since we have iron being higher than copper, the iron is able to displace the copper from the copper sulfate. Since silver is not higher than copper, it is not going to be able to displace the copper from the copper sulfate. And that's why in situation 3, Jaden would have experienced the solution to technically starting to have a faded blue appearance because the copper is now being displaced. Likewise, in 4, the solution is just going to remain blue because the silver is not reactive enough to displace the copper, so the copper is just going to remain bonded to the sulfate. So once it is more reactive, it's going to kick it off and take its place, displace it from the compound that it is in. So that is what iron did to the copper, causing the copper to now basically be on its own. So copper sulfate, if you can think about it, hydrated copper sulfate, and that is in the lab as well, we know that it has a blue appearance. Yeah? So it has a blue appearance. So when we dissolve it in the water has that the water has that blue appearance, faded. And so that would have been the end of the question relating to oxidation and reduction. Were you able to, and again, if you notice, nothing that came up here. What you find is that you see the compound solution C, compound C, and I heard Miss mentioning about the peroxide. And so we didn't touch and we never looked at, you remember I said that you have some compounds that can technically act as a oxidizing agent and also a reducing agent. So if it's with an oxidizing agent, it acts as a reducing agent. And if it's with a reducing agent, it acts as an oxidizing agent. And so that's what C was doing. C can be an oxidizing agent and a reducing agent dependent on who it is with. So once we learn and appreciate the observation, so like I said, prime example, you see where they gave you the test and they gave you the observation, and then for the question they ask us to, explain why, account for that observation, tell us what is happening, and we were able to do that. Not true?
Yes, sir.
So again, thanks for tuning in. I hope this session was beneficial. We are now going to, you can continue your preparation. You can contact us if you're interested in getting a past paper booklet, answering the questions, like, subscribe, and share the video. And again, Mr. Thomas is the name, Buckle Down Tutoring Services. All right, we're going to be moving on to electrolysis, electrochemistry, rather. Thank you.